All right, welcome everybody to section 1.5. In section 1.5, we'll be talking about the integration technique of substitution. But before we get into substitution, I want to describe some common integration mistakes, and we're going to talk about how to avoid one of them for the time being, and some of these others will come up later on in this course. So example 1 is asking us to explain why t squared over 2 times sine of t is not an antiderivative of t cosine of t. So the first thing that I want to do is point out sort of why this is a reasonable mistake to make. If I asked you to find an antiderivative of t, you would tell me that t squared over 2 is one of those. And if I asked you to find an antiderivative of cosine of t, well, you would also tell me that sine of t is an antiderivative of cosine of t. So it looks pretty reasonable here in that we are taking the antiderivative of both pieces of this function, but it's going to turn out that that's not a great way of dealing with multiplication. That is a good way of dealing with addition, since we know that the integral of f of x plus g of x dx is the integral of f of x dx plus integral of g of x dx. So this rule tells us that when I'm adding two functions, I can integrate them separately. But it's going to turn out we don't have a rule that says integral of f of x times g of x dx equals integral of f of x dx times integral of g of x dx. This is not a rule that we have available to us. So let's see why we don't have that rule. And later on in this course, we'll talk about what the actual thing to do is. So in general, if we're checking to see whether or not this function is an antiderivative of this function, it suffices to check what is the derivative of the proposed antiderivative. If the derivative of this t squared over 2 sine of t is t cosine of t, then we're in good shape. We know that this guy is an antiderivative. But if this guy's derivative is not t cosine of t, then we know that this is not an antiderivative of t cosine of t. So here's what we need to check. Is ddt of t squared over 2 sine of t equal to t cos t? So what I've written down here is a question, not an equality. I'm not saying that the left-hand side is equal to the right-hand side here. I'm asking a question if the left-hand side is equal to the right-hand side. In order to answer it, I'm going to compute the left-hand side and see what happens. So the left-hand side here is ddt of t squared over 2 sine of t. In order to compute this derivative, we recognize that we have a product here. We have t squared over 2 times the function sine of t. So remember that my product rule says take the derivative of the first. So this is equal to the derivative of t squared over 2 is just t, and multiply by leaving the second alone, t sine of t. To that, we're going to add, this time we're going to leave the first function alone, t squared over 2, and multiply by the derivative of the second function. The derivative of sine of t is cosine of t. Now that we've taken the derivative, or we've computed the left-hand side, we want to check, is this thing that we've just computed equal to the right-hand side? In this case, it sure doesn't appear to be, and there's no way of manipulating this arithmetic here to make it look like t times cosine of t. If you want to check a particular t value to verify that these two equations are different, you could probably check t equals pi to see that this here evaluates differently than t cosine of t. But in any case, just looking at it, we can pretty easily tell that these are, in fact, different functions. So what we see for our explanation, we see that t squared over 2 sine of t is not an antiderivative of t cosine of t, because the derivative of t squared over 2 sine t is not t cosine of t. And that's enough when we're checking to see if something is an antiderivative of something else. So what's the general lesson that we should be taking from this? Well, the general lesson here is kind of this integral rule, or this non-integral rule that we said. If we're integrating a product, you're not allowed to just integrate the different pieces. You have to use some other kind of technique in order to actually compute the integral. All right, so let's look at a similar example here. Example 2 is asking us to explain why x over x cubed over 3 plus x is not an antiderivative of 1 over x squared plus 1. So this is a very similar question to what we were thinking about in example number 1. We want to simply check, is the derivative of the proposed antiderivative, so is d dx of x over x cubed over 3 plus x equal to 1 over x squared plus 1. So on the left-hand side, I can compute this derivative here. I have d dx of x over x cubed over 3 plus x, and we probably want to think about this in terms of the quotient rule. So here I know my quotient rule talks about my numerator and denominator, so let's give those different colors. Let's see, x cubed over 3 plus x. Great. So my quotient rule says take low d high, so I've got low meaning denominator, x cubed over 3 plus x, d high meaning the derivative of the numerator, so times 1, minus high d low, so high being the numerator, d low being the derivative of the denominator, so this is going to work out to be x squared plus 1, divide by the denominator squared. So in this case, I have x cubed over 3 plus x squared. Doing a little bit of arithmetic here, we can see that my numerator is going to simplify to x cubed over 3 plus x minus x cubed minus x, all divided by x cubed over 3 plus x squared. And simplifying a little bit further, we can combine my x cubed terms, so I should be left with a minus 2/3 x cubed in the numerator. My x's cancel out because I have a plus x and a minus x, and so we are left with this quantity here, over x cubed over 3 plus x squared. All right, so something that maybe we want to notice here is that, again, this is not the same as 1 over x squared plus 1. In part, you can check to see that one of the ways of seeing that these are different, aside from the fact that they look different, is that the left-hand side here, this guy, is not defined at x equals 0 because its denominator is 0 there, but the right-hand side here is defined at x equals 0. So since these functions are at least defined in different places, certainly they are not the same function. So again, we see that this is not an antiderivative of this function because its derivative is not equal to that function. So here we sort of get I guess the moral of this example is that the integral of f of x over g of x, so if we're computing the integral of a fraction, we can't just integrate the numerator and denominator separately. There's no rule that lets us do this. All right, one more example that we want to take a look at here. So we want to explain why sine of pi t squared over 2 is not an antiderivative of cosine of pi t. So again, maybe this seems like a reasonable possibility for an antiderivative because I've taken the antiderivative of cosine and gotten sine. I've taken the antiderivative of pi t and I got pi t squared over 2. But it's going to turn out that, again, this isn't a good way of taking an antiderivative. So let's sort of see why. So again, we want to check, is the derivative of the proposed antiderivative, so sine pi t squared over 2, and I should be using t as my variable here, is this thing equal to cosine of pi t? So we know that ddt of sine of pi t squared over 2, this requires us to use the chain rule, because I have an outside function and an inside function. Inside function is usually easiest to identify. That's my pi t squared over 2. And the outside function is what's left. So in this case, it is sine. So if I'm taking the derivative, we remember that my chain rule says take the derivative of the outside, leave the inside function there, and then multiply by the derivative of the inside. So walking through those steps, the derivative of the outside function here, the derivative of sine we know to be cosine. We're going to leave the inside function there, so that's pi t squared over 2. Now we multiply by the derivative of the inside function, and the derivative of pi t squared over 2 is just pi t. So again, we see that this is not equal to cosine of pi t. In particular, you can evaluate at, cosine of pi t, you can evaluate at t equals 0 to check this one. Because when t equals 0, the left-hand side works out to be 0, but the right-hand side works out to be 1. So these are certainly different functions. So in the end, we see that we can't undo kind of the chain rule by undoing each of the pieces. So that moral is a little bit harder to write down, but the idea is, again, this process of integrating the inside and integrating the outside failed because the chain rule doesn't preserve inside and outside functions. It does something different to them. So next up, what we're going to explore is the question of, well, how do we take an antiderivative of cosine of pi t? And in general, how do we undo the chain rule?